Negative g because we are considering the first motion, so it will be negative. If it's coming down, it will be in the positive direction. That is how it's going to be. So this is going to give us what? From here, you can get t. So t will give us the time taken to get to the end. That is if we define t to be the time at the end. If you define t to be here, then you should know that u is going, and then the final velocity will become 0. Okay, but we are looking at t at the end, so it depends on where you are looking, where your t is. If your t is at the end, then this is how the equation is going to be. So, right, when it comes to this part, all you need to do is so from here, let's finish with the horizontal distance. The horizontal distance is going to be what? Distance is always what? Velocity times time. Okay, but here the horizontal component, okay, is this. We want this horizontal component, so this side is adjacent to the angle, so it's adjacent and then hypotenuse. So we are going to use cos theta is equal to adjacent, which is this one, the horizontal velocity over hypotenuse, which is u, which implies that u cos theta is equal to the distance in the velocity in the horizontal. So the velocity in the horizontal is u cos theta. Because we have only one, it is going to go in that direction. It's not going to be changed by gravity. Gravity is at 90 degrees to it, so it will not have effect on the horizontal. So the horizontal will go like this to the end. Okay, so your velocity that you have here, times your distance, distance that you are going. Okay, sorry, times your time. So the time that is given, okay, so it's going to move with, in terms of the horizontal direction, it's going to move with constant velocity, which is u cos this, okay, because no acceleration is on it, so we won't have, because no acceleration, v will be the same, because there's no acceleration, v will be the same. That is why we don't have v component, so this times t. But remember, that's the horizontal distance, so that's the formula for this. But remember that t, you can get t from the vertical equation. The vertical equation, you can get t when you substitute it from vertical equation. For this part of the equation, if you want to get for the horizontal, for this part of the equation, let's say this is the distance, this is the vertical distance, okay? Your equation here, the equation there, that is s will become what? Because we have initial, let's say S0, we have initial height, so that will be S0. You add on the equation that you have here, which is going to be, because that is what is going to define what you are going to get here. Let's say our time t is here, so this plus, so our initial this, which is this, plus the distance that we're going to get for this one. So given the time and then the u here, we'll put them there. So u sine theta times t plus half negative g t squared. So this becomes the equation. But remember, if you are going up to this point, this becomes 0. So 0 will be equal to this. S0 plus u sine theta t times t plus half negative g t squared. Then we work it out. Because we have put u 0 here, it means you went up and came down. Okay, so that should be considered. You went up and came down. So that t will be at the end. So it depends on where you are looking at your t. That will give you. So that will give you your answer there. As your initial velocity, you are giving the initial velocity. So sometimes you can be asked to find the final velocity. So if you're asked to find the final velocity, how do you go about it? That's the final velocity in terms of the vertical direction. In terms of the vertical direction. Of course, we said the horizontal direction, this u is going to be constant because there's no acceleration on it in the horizontal path. Okay, so that one you can use that one to work things out. The most important part is just get this part well as the basis. Okay, this is the equation. Okay, this is the equation for this. This is what you have. Okay, when it's moving up, it becomes 0 here. This becomes 0 because if you have moved up, it can become 0, and then you have this equation. From there, you can get t. When you get t, you can substitute it for horizontal distance, is this times the time t, then you get it. Right. So let's go to momentum. Let's look at what we mean by momentum. So momentum is your mass times your velocity, by simple definition. Your mass times your velocity, that's your momentum. First of all, you should know the three laws of Newton. Okay, so the first law, the second law, the third law, you must know them. Okay, so the first one, if you are there, let's say you are at this point, you remain there. If you are in motion, then you should keep on moving forever until an external force acts on you. Okay, right. So that will be the first one. So that is the inertia aspect of it. So a body will remain at rest forever. Okay, unless external force acts on it. Okay, and if it is in motion, it will continue to be in motion. It will continue to be in motion and straight line motion, because it will continue to be in a straight line motion unless an external force acts on it. So that the second one is your change in momentum. Okay, the change in momentum. Okay, or rate, that's change in momentum. Is equal to the force that caused that change. Okay, the force that caused that change. Change in momentum will be equal to the force that caused that change. So if the ball is moving, okay, and hits the wall, bounces back, okay, the force that it was coming with mv, let's say mg, when it hits and it's going back is mv. Okay, the force that caused this change in momentum, so F will be the force that caused the change, okay, will be equal to the change in momentum. So m minus mu, this is the change in momentum over time. So the rate of change in momentum over time. This is what the second law defines. Okay, and you know force is also equal to what? Mass times acceleration. Acceleration is there because it's acceleration which is going to change u to v. Okay, so I'm looking at the mathematical sense of the second equation, the second Newton's law. Okay, the third Newton's law, of course, we know for every force there's what? Every force there's there's an equal opposing force. So every force that you do, the force that opposes it, they are equal. Okay, so for every force there's an equal and what? Opposite reaction. Okay, so this goes, if I slap or if I hit this, the force that I use to hit this is the same force that this also impacts in my hand. Okay, but the point is, somebody will ask, if that is so, then why won't you feel pain in your hands? Okay, the point is, I have nerves in my hands. Okay, so when I hit, although it's the same forces that you have impacted on each other, I have more pain nerves in my hands, so I'll feel pain. Okay, so that's it. The other point is, somebody will say, if you look at the earth, okay, if you jump and then you come back to it, you hit it, the force that you hit it with is the same force that the earth also hits your feet with. Okay, the same effort. Okay, but the earth is not going to change motion. It will not be significant, but you may change a lot. Okay, because you are small. So when two bodies collide, the bigger body is most likely going to move with a smaller velocity, and then the smaller body is most likely going to move with a bigger velocity. Right. Okay, so we have looked at the three laws. Okay, first inertia, stand alone forever, go in a straight line forever. The next is what? Change in momentum, rate of change in momentum is equal to the force that effected that change. Okay, and the third one is, for every force, there's an equal and opposite reaction. Okay, that is the point. Yeah, okay. Alright, so that is that for this one. Now let's look at momentum, and then we move on to the next chapter. So having gone through the momentum, we have what we call conservation of linear momentum. Okay, so what we say is, let's say we have this body, then we have that body. Now this is coming, this is also coming. They will collide. Okay. So this was coming with mass. Its mass is this. It was coming with a velocity of u. Let's say mass 1 with velocity u1. This was mass 2 coming with velocity u2. Okay. So when they hit each other, they are going to move. This is going to move with mass 1, still mass 1 velocity. Let's say u2. Okay, because you have said this is u2, you can just go to v and say maybe v here, okay, v1, and then this is going to move. It's going to be. It's also going to move. It's going to be the same as mu v2. It depends on how you choose. Just be sure, conscious of the letters you are using. Okay, then you can do it that way. Somebody can also use, say here u, and then make this one v, so that this is m. It becomes mu2. It becomes mv2. It depends on how you choose. But what we are saying is, in conservation of linear momentum, momentum is always constant. It means the initial momentum is equal to the final momentum, momentum after collision. So momentum, we said, is the same as your mass times your velocity. Okay, so initial momentum, let's see. So initial, the sum of the sum of momentum of the two bodies. Okay, so that will be m1 u1, m1 u1. Okay, if you do that, as you go along, you should get the same thing as the first one. Now, if you look at what we are saying is the sum of the initial momentum, or momentum. Okay, this plus m2 u2 will be equal to m1 v1 or m1 v plus m2 v2. Okay, right. So in this case, this is what you have. This is the equation. This is the sum. This is the equation we are talking about. Good. Now so this equation always stands for linear conservation of momentum. It's always stands. Now we have another part. So it means that whatever you do, you choose one path. You can decide to choose this direction as positive. So anything going in the opposite direction becomes negative. So m1, the momentum before, this is the sum of momentum before. So this is before, and this is after. Okay, but remember the directions. Okay, now if they were coming in the opposite direction, if you choose this one to be the positive direction, then this one would be, so that this u would then become minus u. Okay, right, and then it goes on. So after collision, if you are told one move that direction, that move the other direction, depending on the same direction. So this direction is positive. You make sure you take that into account in giving the magnitude, the V's. Alright. But remember that even if they move at an angle, maybe after they collide, the two can stick together. If they stick together, then that is what inelastic. Okay, it means there's the movement is then more or less more energy is changed. Okay, at the end. Okay, we have lost a lot of energy. Okay, then that is inelastic collision. Now, if they hit and then probably exchange velocities, the same energy before is now what is happening afterwards. Then that becomes elastic kind of collision. Okay, but if you are looking at momentum will be conserved in both. Now, if after collision they are moving at an angle, you must resolve. Let's say if after collision is moving this way, this is also moving that way. You must still look at the direction that you have chosen. This is positive, and then that means get their components in this part. So if there's an angle here, get the component of this velocity in this one, as well as in direction, and then put them in the after the collision. Okay, So if it's also an angle like that, resolve its direction. So you resolve it component. That means you can hear it will be cos theta is equal to, so this is the after it moved, the after velocity. Let's say v2. So cos theta is equal to what? This and that. So we want this motion. Okay, that's the horizontal motion over v2. So that from here v2 cos theta is equal to h. Okay, so we have resolved it. That means we have this component in this part, and this is what we are going to use in the conservation of linear momentum equation. So when they move at an angle, just get their velocities in that same horizontal and then consider the direction. That's what I mean. So this becomes the velocity at a collision, not just this. That's the velocity, the actual velocity in the linear, in the same path as after the collision. And you put it there and then waiting. But usually they will tell you in the same, they will move in it. So that to make the question simple, you'll be told they didn't move in an angle to the initial path. So that in that case, if there's no change in angle, then it's the same thing that holds. Right. Okay. We have talked about how to change, convert, what do you call it, a component into component in mathematics. Okay. The same thing principle can be used. So this is what I mean. Let me get it well. Let me just be brief about it. Then we go on. So all that I'm saying is that you just need to get your M1 U1 plus M2 M2 U2 is equal to M1 V1 plus M2 V2. Okay, that's it. So you put the values in, always note the direction, choose a particular direction as positive. The rest, if you are going opposite, is negative. So this one, when you work things out. But in the second one, sometimes when they are coming, it's like that. Then after collision, maybe one ball, this one moves like that. Okay, and then this one also moves maybe like that. This was the initial path direction. Okay, then what you do is you here, when you have something like this, what you do is you find this angle, resolve this one, find the component of this velocity, the component of this in this angle. So this will be cos theta, and the velocity that you have, let's say v1. Okay, this is mass 1, this is mass 2. So this one is also moving with v2. So this will be also theta, and this will be adjacent, and then this will be adjacent, and then the angle, and then hypotenuse. So it will also be cos theta. So this will be v2 cos theta. Okay. So in that case, before will be m1 u1 plus m2 u2 is equal to, now it's going to be m1 times each velocity is going to be what? v1 cos theta plus what? m2 v2 cos theta. But remember, when you do it, when you resolve it, if it is in the same direction as the first one, then it's positive. Assuming one went this way, then of course the velocity will then become negative. You resolve it and it becomes negative. Okay, this is what I mean. So this is a simple one for simple momentum, linear momentum conservation. This is where they move at an angle. This is the second one for where there's an angle change. Right. So that is that. Now let's look at how to get kinetic energy. Let's say the body is here, it's moving. Okay, how to derive that? We know force from definition. Okay, it's the amount of pull that will make a 1 unit mass. Okay, in terms of measure, 1 unit mass accelerated by, give it an acceleration of 1 meters per second. Okay, so the force in quantity will be anything, the measure that will cause 1 kilogram to accelerate by 1 meter per second, 1 meter per second square. Okay. So you see that force will then be equal to what your force is then going to be proportional to what your mass times your acceleration, for which force is going to be equal to k mv. But we said because we said by definition is 1 kg by 1, then this constant is going to be equal to what? And this is 1. This constant is going to be what? K is equal to 1. And therefore, force will be equal to mass times acceleration. Right. So that is what we have at the back. Now let's see how we can use this one in this deriving the kinetic energy. So here is the mass, and it's moving with a certain velocity, initial velocity v. Okay, if it is moving with constant velocity, let's say v, our work done is given by force times distance. The force that you are using over a distance that you move is work done, and it's measured in that's energy, okay, joules. Okay, right. So work done. So the mass, what is the force? The force is going to be your mass times your acceleration times your distance. Okay, we have already said that acceleration is equal to v minus u over 2. Now in this case, the body is moving with constant velocity. If you are moving with constant velocity, then of course this will go off and there is no acceleration. But we are saying that there is an acceleration in this case. Okay, then that will mean that you started with an initial velocity, let's say v, maybe 0, initial velocity 0, and then by the time you got to your final velocity is v. So we started with 0, and then we got to the final velocity v, so that u is equal to 0 and v is equal to v. In this case, if you put it here, we're going to have, from this equation, we're going to have the work done is going to be equal to what? Your mass times your acceleration, which is what? V minus 0 over t times the distance. The distance is s. Okay. Now, what's going to happen? So we have a mass like that. So this mass times the change in the acceleration is initial, final minus initial over t, because we know this, this is not 2, this is t divided by t, so we put it there. Okay, right. So we are here, and we so this is s. We have this m v minus this over t times s. Now s, how do you define s? S is the distance. M v minus 0. Alright, sorry for the break. Okay, so at this point, this is over t times s. Distance is also given by your average velocity times time, which is the same as u plus v over 2 times t. So let's substitute this one here. So we're going to get what? U plus v over 2 times t. Now let's simplify. We're going to get m v over t times, this is u is 0, so it's going to be v over 2 times t. Okay, that's the work done. Okay, but this is work which is being done, the body is in motion, so we can say it's kinetic energy. And this is going to give us what? It's going to give us v times v is going to be v squared. So m v squared is over 2 over 2. T will cancel t. So this becomes the equation. This is what we write as half m v squared. So that is the kinetic energy. Right. So let's look at another body. Let's say this is a big body. Then there's a blast. A blast and then gives of this, gives of that. So the same conservation of momentum is used. Initial momentum. M1. Let's say this is M1, U1, M2, U2. So M1, its initial velocity was 0 times 0 plus M2, its initial velocity was 0 times 0. Then after the blast, they are now going to have velocity. So M1 U1 plus M2 U2. So in other words, this is going to be 0 is equal to M1 U1 plus M2 U2, which will mean M1 U1 is equal to, if you bring this one across the equal sign, or you can bring this one, any of them, is equal to what? Negative M2 U2. That's what it means. Okay? Of course, that would mean if we assume the blast on the same path that we have chosen. So that will be one conservation of linear momentum, what you can do. So if something blasts, you can just easily get it, okay, from this order, okay. Initially, that will be 0. Initial momentum is 0. After the sum should be that. Okay, all right. So this kind of equation represents something like we have two bodies here. Okay, let's assume it's like two bodies. We can assume this one to be gun, the gun with a bullet in it. Okay, right. In that sense, it's typically fits this equation. Let's see, we have now when this is short, it's going to move with a certain velocity. The initial velocity is the gun, or let's say m gun, okay, its initial velocity is 0 plus the bullet plus m bullet 0 is also 0 becomes what? When it is short, this is going to mean m gun moves back, will move back, or let's assume we don't know it moves with a certain velocity. This also moves with a certain velocity. Because this is 0, we get what? mgv plus mbv. Now this will cause and become negative. So it means that they will move in the opposite direction. Okay, that is why you get a record. Opposite direction. Okay, and this is what this seeks to be here. Okay. Right, so this is a good example of the bullet and then the gun kind of momentum, linear momentum kind of a thing. Let's look at another one from where we were looking at. If you have this, let's say, then there is a blast, this goes that way, this goes that way. Remember, you have to resolve them. So initial is 0, okay. You have to resolve them. You resolve this one in this direction, resolve that one in that direction, okay. And then of course your masses times your change in other mass and change in whatever the mass that it went through. Now because this wasn't the collision, we can assume, of course, just before the initial, there was no movement. So now let's assume in terms of energy, this moves with mass n mass 2, the kinetic energy will be inversely proportional to the mass. Okay, so the smaller mass, for energy to be conserved, the smaller mass will rather move with a bigger velocity. So the smaller mass moves with a bigger velocity, and then the bigger mass moves with a smaller velocity. That's the analogy I want to give in this case. Right. Alright, so for the 3, we have exhausted that part. Now let's look at another thing. Here we'll come to it.